Math and Beats. This video is all about indeterminate powers and how they relate to L'Hopital's rule in a Calculus 1 setting. Let's look at these indeterminate powers. All right, so what is an indeterminate power? Well, they're going to occur when we have a limit of the form right here, and that is limit as x goes to some location a of a function of the form f of x to the g of x power, and in which one of the following happen. So three different types of situations. Remember, keeping in mind here we have the limit as x goes to a of f of x to the g of x power. So either f of x goes to 0 and g of x goes to 0 as x goes to a. So in this case, you would get the form 0 to the 0. So that is one type of indeterminate power. What is that? We'll have to figure out. Another form would be as f of x goes to infinity and g of x goes to 0 as x goes to a. So what kind of form is that going to look like? Infinity to the 0. And finally, if f of x goes to 1 and g of x goes to infinity as x goes to a, then we get the indeterminate power form 1 to the infinity. So in the first two, it seems pretty intuitive, I think, that, yeah, that's kind of funky, right? 0 to the 0, that's not something that is defined. And the second one, infinity to the 0, if the base is growing gigantically big and the power is getting close to 0, then what really is that? Now, sometimes in the third one, people might think, oh, that might just be equal to 1. But as we're going to see, that's technically not true, and we're going to do an example of that in this particular video. Now, the question is, if we have one of these situations, how are we going to go about figuring out what the limit is actually equal to? Well, let's see how. Now, first of all, each of those forms do not have the indeterminate form 0 over 0 or plus or minus infinity over infinity. Those are the two forms, of course, we need in order to apply L'Hopital's rule to our limits. But the ones that we have in this video, the indeterminate powers, don't have that form. So we cannot use the L'Hopital's rule directly here. Rather, again, we're going to have to manipulate the limit so it becomes one of the indeterminate forms above, and then we can apply L'Hopital's rule. So let's go ahead and take a look at a couple of examples here. Let's find each of the following limits. The first one that we have in part A here, we're given the limit as x goes to 0 from the right of the function x to the x. Now, we can see as x goes to 0 from the right, this is going to approach 0 to the 0. And so we have one of those indeterminate powers, as we say. Question is, what do we do? How do we go about this? Well, one way to think about this is possibly using a logarithm to help manipulate this limit. One thing to note that for values of x that are positive, we have that x to the x is going to be positive. So that's good, because if we need to take a logarithm, then we know it's going to be defined. Now, moreover, let's just pretend that this limit exists for the time being. Assuming it exists, right? Then we can call this limit L. And that is, set the limit as x goes to 0 from the right of x to the x, just equal to some number L, whatever it might be. Then it would follow that if I take the natural log of L, then that's the same thing as taking the natural log of the limit as x goes to 0 from the right of x to the x. But by properties of limits with composite functions, that is the same thing as the limit as x goes to 0 from the right of the natural log of x to the x, which is the same as the limit as x goes to 0 from the right of x times the natural log of x. So what do we got? We got that the limit itself, which we're calling L, whatever that might be, is this. However, the natural log of the limit ends up being equal to this right here. The limit as x goes to 0 from the right of x times the natural log of x. Does that help? Well, if x now goes to 0 from the right, we can see that this is going to go to 0 times a negative infinity. And that is an indeterminate product form. So if I go ahead and rewrite that as the limit as x goes to 0 from the right of the natural log of x divided by 1 over x, using that technique of dividing by the reciprocal of one of the factors when we have an indeterminate product, then we can see now this is going to go towards negative infinity in the numerator and infinity in the denominator. And now it has one of the indeterminate forms for which we can use L'Hopital's rule. So let's go ahead, use L'Hopital's rule, and what do we get? We get the limit as x goes to 0 from the right of derivative of the numerator 1 over x, derivative of the denominator negative 1 over x squared, and that is the same thing as the limit as x goes to 0 from the right of negative x, which is equal to 0, of course. So what does that all tell us? What did we just figure out? Well, we didn't actually find the limit we're after. Instead, what we found was the natural log of the limit. So over here on the left, we figured out that the natural log of the limit that we're trying to find is equal to 0. However, we're after the limit itself, and thus it should follow that L should be equal to e to the 0, which is the same thing as 1. And there is our value of our limit here. So a big takeaway of this, if you have, at least in this form, an indeterminate power of 0 to the 0, and assuming that all the good things happen, then go ahead and take a logarithm of both sides by setting the original limit equal to some value, say L, some variable, whatever it might be, and then manipulate the natural log of the limit. From there, you will encounter some type of other situation. In this case, it was an indeterminate product for which we went ahead, turned it into indeterminate form, and found that limit being 0. And then going backwards, we need the limit. So exponential e base to that power of 0 gave us 1. Let's look at one more example here in this video. Here's another one. Limit as x goes to 0 from the right of the function 1 plus sine of 4x, all to the power of the cotangent of x. Now what happens here? Well, notice that the base function, this thing right here, as x goes to 0 from the right, well, sine of 4x is just going to go to 0, so the base goes to 1. In the power here, we have the cotangent. Now remember, the cotangent function, which is 1 over the tangent function, is the same as the cosine of, say, x divided by sine of x. And as x goes to 0 from the right, that cotangent function blows up to infinity, if you kind of visualize that graph again in your head. So this actually goes to 1 to the infinity power. And so here's going to be an example that shows this is not necessarily going to be equal to 1. You've got to be a little bit careful here. Perhaps there's a connection with the number e, remembering the definition of e. So again, you know, when we are close by to 0 on the right, if x is positive and say, quote unquote, nearby x is equal to 0, then what happens? Well, sine of 4x is going to be clearly positive, and moreover, the cotangent of x is also going to be positive. So the entire quantity is a positive number raised to the power of a positive number, which is positive when we're close by to x is 0, but on the right side of 0. So we can go ahead and take the natural logarithmic game that we played in the previous example again. Let's go ahead and set this limit L, or should I say the limit equal to L, limit as x goes to 0 from the right of 1 plus sine of 4x to the cotangent of x. And then from there, we'll go ahead and take the natural log of both sides there, so that the natural log of this limit that we're after is the same as bypassing that first part, right? Natural log of the limit is the limit of the natural log here. So limit as x goes to 0 from the right of the natural log of 1 plus sine of 4x, all to the cotangent of x power. Simplifying that gives the limit as x goes to 0 from the right of the cotangent of x times the natural log of 1 plus sine of 4 times x. So we manipulated it so far using our logarithms. Question is, what happens now? Well, let's think about it. As x goes to 0, right here, we're at this step, right? From the right, x goes to 0 from the right. The cotangent is still going to be blowing up to infinity, right? So this is going to go to infinity times something, but what is the something? Well, notice that as x goes to 0 from the right, sine of x goes to 0. So this whole piece is just going to be natural log of 1, which is 0. So again, we have an indeterminate product occurring in this situation. And we'll go ahead and divide by the reciprocal of one of these functions. Now, it won't matter which one you use, but there's usually a better choice. Because the natural logarithm has a composite within it, right, natural log of 1 plus sine of 4x, if I divide it by the reciprocal of that, it'd be 1 over the natural log of 1 plus sine of 4x. And that might be a little, involved when we go and hopefully apply our L'Hopital's rule and differentiate it. So I'm going to go ahead and divide by the reciprocal of the cotangent and rewrite this as the limit as x goes to 0 from the right of the natural log of 1 plus sine of 4x, and then divided by 1 over the cotangent of x. But, of course, 1 divided by cotangent of x is tangent of x. So this is the same thing as limit as x goes to 0 from the right of the natural log of 1 plus sine of 4x, all divided by the tangent of x. So now we're at this spot where we see a quotient. The question is, does this quotient take on the form that's indeterminate, and we could apply L'Hopital's rule? Well, in the numerator, again, as x goes to 0 from the right, numerator is going to go to 0. And in fact, in the denominator, as x goes to 0 from the right, the tangent function also goes to 0. So now we have it in the form that we want to use, and that's the indeterminate form 0 over 0, for which we can go ahead and apply L'Hopital's rule. So let's apply L'Hopital's rule here. And this is going to be the limit as x goes to 0 from the right. In the numerator, chain rule, derivative of the inner function is going to be a 4 cosine of 4x, all divided by 1 plus sine of 4x. So that's all the derivative of the numerator. And the derivative of the denominator, derivative of the tangent function, is the secant squared function. So now we're dealing with this. So go ahead and clean this up just a little bit and write it as the limit as x goes to 0 from the right of 4 cosine of 4x, all divided by secant squared x times the quantity 1 plus sine of 4x. Now, what happens? Well, let's figure it out. As x goes to 0 from the right, the numerator is going to go to 4 here. And in the denominator, as x goes to 0 from the right, this secant squared, which is 1 over cosine squared, is going to go to 1 times another 1, since sine of 4x goes to 0. So this limit ends up equaling 4 here. However, remember, again, this is not the actual limit. This is our natural log of our limit. And so over here on the left, we have that the natural log of our limit that we're after, L, is equal to 4. So it follows that the limit that we're actually after must be e to the 4th. And so you look back up here, all right, that indeterminate form, indeterminate power, that is, of 1 to the infinity didn't equal 1, right? That limit is actually e to the 4th. There was e involved. And there you have it. So now you have seen 2 different examples of indeterminate powers, and hopefully that does the trick. But that is it for this video. So when dealing with one of the 3 indeterminate powers, you can take on the approaches that we took on in this video, so long as everything is defined and the conditions work out the way they should. And so that's it. Until the next one, it's Math and Beats, and I'm gone.